This is Chemical Engineering 2450. Make sure you're in the right class, also known as Numerical Methods, or the infamous Numerical Methods, the most feared class on Earth for some reason. But hopefully that's not what you will take out of this course when you're done with it. Partly because we've introduced some really nice changes to the course throughout the years and to make it easier and more manageable for all of you. Okay? Before I get going, I want to introduce you to two of your TAs. The third one will be showing up next week. We will have two TAs for the help sessions. We will have 4 help sessions if things go well, and I'll talk about that in a second. So there will be 2 TAs who will be working with the help sessions and helping grade the homework, and we will have 1 Python tutor for you guys. Kevin and Bailey, will you come up, please?
Woo, Kevin and Bailey!
So Kevin, he was one of my disciples in Numerical Methods in 2018, and so was Bailey.
Actually, I was the year before.
2017, that's right. That's right, 17, a little bit older. It doesn't show, but you know. So Kevin is going to be your Python tutor. He will be sitting in a corner in the help sessions once we get that figured out. Maybe in the center, we'll give him a nice round table. He will work with you one-on-one. And we'll talk about the cap that you will have. You'll probably have about 10 minutes with him. You'll come with clear questions, and he will be able to help you with your programming questions. Anything from, how do I do this, to how can I improve this loop? Can you help me find the bug, etc. But exclusively Python-related questions. Bailey Tibbet, she will be working with the help sessions and or grading the homework. And she will also be answering the email help for this class, and also a new feature I'm introducing this semester, a forum. So we're going to try out having a forum where you guys can talk to each other, and we will be administrators helping you out, ask questions and answer questions. So remember their faces. There will be one more TA who is my PhD student. He's a researcher doing his PhD in my group. Moqbel Karam, he will be coming in next week. He's out of the country right now, and I'll introduce him to you next week. So be nice to these guys and feel free to channel your frustration and anger to them, not to me, okay? And they will channel the frustration and anger or the positive and the kudos to me, okay? So thank you very much, Bailey and Kevin, and you can head out your way if you want. Okay. Oh, very nice, very exciting. Okay. The fun thing about being a professor, the interesting thing about being a professor is that you all remain the same age every year, while I grow older. Every year I receive the students with this at the same age, essentially. I find that rejuvenating and interesting. Anyway, so let's go ahead and clear out some administrative stuff out of the way before we get our hands dirty with this course. So this lecture is fairly introductory. I am supposed to have a nice, clear microphone recording. Unfortunately, I just realized that this transmitter does not fit on this dongle, and I need another dongle. So the recording will be a little bit poor quality today. And I typically move around the board here, but I'm going to try to stay close to the computer to record through the built-in microphone. Okay, administrative stuff. I will be using, you will be looking at 2 websites to deal with this course. My website, Tony Saad. Oh, first let me introduce myself. My name is Tony Saad. The way you pronounce that is Saad. Ironically, some people pronounce it sad, but the sad irony is that it actually means happiness in Arabic. So anyway, you can call me Professor Saad, Professor Tony, Dr. Saad, whichever you prefer. And I will also be using Canvas. If you haven't signed up already to Canvas, please do so. I will use Canvas exclusively to send announcements and post homework and collect your homework submissions, okay? And that's all. The lecture notes and the recordings will be posted on my website, tonysad.net. And there's a menu item up there called Numerical Methods course. You click on that, you'll see the entire syllabus details. I'll provide you with lecture notes, the YouTube videos, Jupyter notebooks, whatever. I see some familiar faces. We're going to follow the same paradigm we followed in 2018, and we're going to do it a little bit better this year. Okay, so the recorded lectures will be recorded and posted on my website, but I'm doing a YouTube channel this year. It was very successful. Last semester I taught graduate fluid mechanics, and I created this YouTube channel, and we received a lot of, we had a lot of impact from outside the university as well. So if we want to make an impact outside the university, we're going to go with YouTube this time, and it'll be easier to all of you. You all have YouTube on your phones and tablets, so those will be posted there. And you click on the link, it will just take you over there. There's nothing right there right now, but we'll start posting essentially after class. Email, I will send you, I will use your email, through Canvas. I'm assuming you signed up with your utah.edu email, so make sure that email is up to date and you're able to look it up on your phone and your laptops. Homework, okay, assignments posted on Canvas, as I just mentioned, and submissions will be also collected on Canvas. We will talk about the type of submission you will submit. We will be dealing exclusively with what we call Jupyter notebooks, soon to be introduced. Those essentially are a really cool way to combine text, images, and programming in one file. In previous installments of the course, students had to solve their homework using MATLAB, and they put it in a MATLAB file, and then they would typeset their results in Microsoft Word, and then they would bundle things together and upload them, and then one file would be lost, one file would be an older version. You know how we all version things, version 1, version 1.1 today, version 1.1 underscore January 16. So, I don't want to deal with that stuff. So you will have a platform. So imagine you're typing like in Microsoft Word, but you can also program in Python and execute your code in the same file. So that's the power of the Jupyter Notebook. We introduced that in our department about 3 years ago since I took over this course, and it's been sensational ever since, and those who have worked with it in the past will testify to that. However, I will still accept submissions with MATLAB or, I don't know, Visual Basic, whatever, but I will not be able to provide programming help over there, nor the TAs. So you will be on your own. If the code doesn't execute, I'm going to assume that it's not working. So I advise you to try to switch gear and jump on the bandwagon of the Python revolution, and I'll try to excite you about that in a few slides. There's a lot to talk about. Like, my mind is very nonlinear today because there's like so many things to talk about. However, so let's follow with these bullet points. I recommend that you work together, you sit together, go grab lunch, grab coffee, talk about homework, but try to do your homework yourselves. I always catch cheating. Sometimes I act on it, sometimes I don't, because in the end, you are adults. I'm going to treat you as adults, and you'll only be hurting yourselves if you copy, because you don't learn anything. And in the end, when you're out there in the world on your own, it's gonna catch up. It's gonna catch up with you. So work together, but don't plagiarize. Don't copy other people's work. Even if if you see a piece of code by your colleague, try to kind of reproduce it with your own kind of understanding. Don't just copy and paste and change symbols. Okay, try to change variable names. Understand what your colleague did. That's okay. I do programming that way. I learned programming that way, specifically coding. And I'll tell you about the difference between programming and coding. I always look up things on the internet. I get the code, I try to understand it, and then adapt it to what I want. So that's completely legit. Do not procrastinate. And so once you get a homework, once you look at the lecture, go review the lecture notes. I'm going to try to post the lecture notes before class so that you have a chance to look at the notes before coming to class. That's very useful because there's this thing called psychology of the mind where if you are exposed to the thing, even if you don't understand it, but just looking at it a few times before you hear about it, for some reason it becomes easier. I had a math professor when I was doing my PhD, and I did my PhD at the University of Tennessee Space Institute. We're doing rockets and things. Actually met an astronaut over there, but I had a math professor right across my desk, my office, and his name Boris Kupperschmidt. He passed away a few years ago. He's a famous guy. There's like a Wikipedia page about him and the Kupperschmidt equations. And he told me one thing. He told me two things that I take to heart. But one of the things is that when you read a journal article, a research paper in math, just don't try to understand it from the first read. Just look at the symbols. Go sit, grab a tea or coffee, and look at the symbols. You see these summations and sigmas and etas and these integrals. Just look at the symbols. One time, two times, three times, and then sleep over it. And then the next day, try to read it. You'll be able to comprehend it better. So even if you don't understand the content of the lecture, okay, if I post it ahead of time, go ahead and just look at it, browse through it, take you 5 minutes, do it again, kind of look at the bullet points, do a speed reading, okay, and then come to class, and I guarantee you that you are more likely to understand the content than not, okay? Typically, I assign homework on Thursdays, and the homework will be due 10 days later on the Monday, 10 days later, okay? Because on the Tuesday after that, I will solve the homework with you in class, or kind of the hardest problems in the homework in class. So then you'll get a chance to look inside my mind how I try to approach solving homework problems, okay? My office hours are today after class from 3:30 to 4:30, or by appointment. Just send me an email to my personal email address. More on that in a second. My office is in CME 115. That's a temporary office. This building is the Civil and Materials Engineering building. It's just south of this building, or you can look it up on the UMAP, okay? CME 115 on the first floor. Make an appointment, or if my door is open, just feel free to come on in and we can talk. But please come with clear questions. Oftentimes, students come in and they have like this huge folder and they're jumbling notes. We're like, I wanted to ask you about this. Where is it? And that's 5 minutes. Okay, so be ready with a clear question. Come in, and we will be both very, very effective at answering your questions. Okay. This is my work personal email address. tony.saad@kennedge.utah.edu. Use this for personal communication. Do not use this for homework help or class help. I'll give you another email for that kind of help. Use this for things like, hey, I have a headache today. I'm maybe 15 minutes late to the exam, or someone, I have a family emergency, etc. Just send those or any other concerns, personal challenges, things like that. Or if you want to make an appointment, use this email for those things, okay? Help sessions to be determined, but that is going to be dependent on you going on Canvas and clicking on the doodle poll and putting in your availability. So we couldn't set up the help sessions. This is the first time we offer this course in the spring semester since 2009. And so we don't know what times work for the help sessions. So I'd like to get some feedback from you to see what times you are most available. So we'll create these 4 help sessions to try to cover everyone. So please try to get to that poll tonight. It's set up as an ungraded assignment on Canvas. Go on there and there's going to be Monday, Tuesday, Wednesday, Thursday, Friday. Just pick the times where you are available in half-hour increments, even if it's just half an hour. You can come in early on in the session and then leave. We'll try to make the sessions about 1 hour long, okay? Okay, next, teaching assistants, Muqbil, Karam, and Bailey Tibet. You met Bailey today. Python tutor Kevin. This is the email for help questions about the homework and other things you are having challenges with. So all the TAs, myself, have access to this email. So we'll try to get to it. Sometimes we don't. Then spam us if we don't, or just send me an email directly to make an appointment and then come and talk to me. okay, because, it happens. 2450help@gmail.com. Okay, the ICC in MEB 2285, this is where the computer lab is. If you don't have a computer or are having a hard time, or need a place where you can sit and, do homework calmly, go to the ICC, and we will likely have the help sessions over there, depending on availability. There is no specific textbook for this course. I'd like to write a textbook and give it to you for free eventually. But until we get there, we're going to be based on my slides that I'll give to you. And those slides are based on this book by Chopra and Canale, Numerical Methods for Engineers. If you want to buy it. I'll try to post chapters and problems from it as we go along, essentially selections from the book. But I think my notes are enough for you to understand the material. Okay, so I've tried to synthesize the knowledge as much as I can. Okay, and this is the forum I was talking to you about. This is the first year I'm trying this. I think it'd be really cool if you all sign up to these forums and you go and and you can feel free to have fun also on the forums. I'll probably create a category for like just random stuff where you can chat about things. But you have to sign up with your utah.edu email, otherwise you will not be able to register. Okay, so this is only open to University of Utah students. You'll see multiple forums in there. Go to the Numerical Methods 2450, but there's also a forum on Python, also for Python-related questions, okay? So feel free to try it, and we can start building a community so that future students can also essentially have their questions answered by one of you in the past, okay? All right, so numerical methods. What are numerical methods? When I tell you numerical methods, what do you understand? Yes?
It's kind of like trying to find an unknown function by telling a computer that these are like a set of slopes, so that the derivative is something, and that a set point in that function, and then you try to have your stab at what it might be.
Okay, that's one specific application of numerical methods.
Solving things discretely.
Okay, what is this?
Like
What
plug in
discretely,
a number,
like, are you like?
you plug in a number, then you get a number out.
Yes, yes. So that's the keyword, discretely, and I'll come back to that. Any other takers? Numerical methods.
It is kind of like sequentially is what I think, like, you take the last one and add to it or something.
Okay. Yes.
Well, think about I took Cody for this class and she made certain plus minus do the wrong cut up by hand.
Okay.
So just being able to do that on a computer and approximations or something.
Yes. Okay. Okay. So all your answers are correct, and there's no one single definition of numerical methods. It's just a very big umbrella. It's like the word disease. It's like a big umbrella of different things that can happen. Numerical methods are essentially a way of solving, using computers to solve governing systems of equations or equations that govern physical mechanisms. So the first step in approaching any scientific or engineering problem is to come up with a model. And that model essentially synthesizes the physics. So for example, you're boiling a lobster. We're going to come back to the lobster problem. What's going on with the boiling of, for those who took the class with me before, they probably remember the lobster story. But you're heating a lobster, and there are physical things going on when you're heating the lobster. There's heat transfer. You're boiling it. There's convective heat, what's called convective heat transfer, or you're putting it in the oven. There's radiative heat transfer. So you're starting to develop the physics of the model, and then there's going to be a point where you have to write a mathematical expression, okay, for those physics. So it could be a partial differential equation, an ordinary differential equation, a system of equations, a nonlinear equation. All of those, they're just a mathematical model that expresses the physics. The next step is to take this mathematical model and solve it. You could solve it by hand if you can, if it's simple enough. But for the vast majority of applications, these problems are so complex They're nonlinear, they're difficult to solve. We need computers to solve those equations. Now, how do we go from the equations to the computers? We have to discretize. We have to do this thing that your colleague said, discrete. We have to do them discretely. Essentially, that's the analogy between analog and digital. Analog is like a continuous signal. Digital is a discrete signal. That's the same thing we do with numerical methods, is we take continuous equations and turn them into discrete flow points and solve that on a computer. So to give you a perspective with your chemical engineering education, typically all engineering and physics relies on fundamental conservation laws. So those are conservation of mass, conservation of energy, right, conservation of momentum, things like that, right? That's how nature operates. If I give the example of the hose of water in your garden. You go open up your faucet and you have the hose, there's water coming out. What happens when you put your finger on the tip of the hose, right? Start closing the opening. The water is going to shoot out. Why does it shoot out? Well, even more fundamentally, it's because of conservation of mass. So there's a certain mass coming out from this opening, okay? Now, as you close the opening, that same mass needs to still come out per second. So since you've decreased the opening, to have that same mass come out, it needs to come out faster. And that's an example of a fundamental conservation law. Okay, so you will learn in your chemical engineering education, this is not a class about conservation laws, you will learn those in heat transfer and thermodynamics and fluid mechanics, etc. But we typically start, whenever we're trying to untangle a problem, we start with what we know about the fundamental conservation laws, and then we come up with different models. So for example, heat transfer, we need a model. There's a Fourier model for heat transfer. There are other models out there. You come up with a model, and then you come up with what we call an algorithm, which is essentially a set of steps you need to take to obtain an answer. What you know so far is solution by hand. For very simplified problems, you just pencil and paper and a calculator and you come up with a solution. Now, numerical methods is another way to plug computers into the algorithm and to be able to solve the more complicated problem. And this is where Python, Excel, and whatever comes in. You will learn fundamental conservation laws, approximations, and models in all your other chemical engineering courses. And you've learned this in 1703. Who's taken 1703? Okay, pretty good. All right, so you've probably been exposed already to Python and Excel and whatever other tools. Numerical methods falls in right here. Is that the problems we're gonna solve are gonna give you the mathematical expression of the problem. In your later courses, you will learn how to derive that mathematical expression. So going back to the lobster example, I'm going to show you how we can derive a governing equation for how the lobster temperature changes over time. But you're not responsible for deriving that equation in this class. You're responsible for solving it. I'll show you how to solve it. In other classes, okay, you're going to be responsible for deriving that equation. So in a way, we're taking a top-down approach. If you want, we're starting from the end and going backwards to see kind of what numerical methods can do. Okay. I also want to give you an idea of where numerical methods can lead you. So my entire career, my research is in an area called computational fluid dynamics. So it's fluid dynamics, solving fluid dynamics problems using computers. The equations that govern fluid flow, fluid dynamics, gas dynamics are very complex equations. They're known as the Navier-Stokes equations. They are a set of at least 4 nonlinear coupled partial differential equations, very complex to solve, okay, and they require a lot of computational power. So that's what I do. That's my area of research. And so I figured I'll show you an idea of kind of what my group does. We call the Utah Computational Engineering Laboratory, just to show you that what you're learning here is just the first step towards doing the things that we do in my group. So I always like to start by summarizing the scientific method. Let's see. Let's put it here. Is better? Yes. Okay. So typically, the standard scientific method, we learned that you first look you first do an observation. You see something happening. So for example, things fall to the ground. That's what Newton saw and observed. That's what others have observed before him, Kepler, Galileo, etc. Things fall to the ground. And then you come up with a hypothesis or a model to say, why do things fall to the ground? So Newton hypothesized that there is a fictitious force that attracts things between two bodies. You know, the larger the body, the larger the attraction force, and he called that gravity, gravitational force. And he posited a model. He said that the force of attraction is proportional to the mass times the acceleration. That force between the two bodies is F equal m times the acceleration. And then he went ahead and did experiments. So that's also what Galileo did. Doing experiments on trying to measure that force, or you specify the force, and you have, you know, the mass, you get the acceleration, and then you refine. If that experiment shows you that your model, there's something wrong with your model, then you go back to your hypothesis and say, oh, maybe my proportionality constant is incorrect. So let me modify that a little bit, and then run new experiments, and so on. Okay? And that's fine for things that are essentially fundamentally simple. Like, you know, something falls to the ground, you can isolate the entire world from that and just look at the apple falling to the ground. That's the famous example we show Newton with the apple falling on his head. Okay. However, how do you experiment on things that are absolutely crazy, like an exploding star, like a supernova? Okay? Trust me, there's nothing that my heart would love to see more than, you know, doing a supernova in a lab. But, you know, that'd be probably the last thing that I would see. But how do you experiment on a supernova? How do you run an experiment? That's a supernova. Seriously, you can't. The only way to do it is to do a simulation on this. Is to take simple models, gravity plus radiation plus fluid dynamics plus reactions plus magnetohydrodynamics and so on, put them all together in a simulation and simulate a supernova. Just go on YouTube and do type 1a supernova simulations, and you see some of the most beautiful, or just supernova simulations, some of the most beautiful simulations giving you insight into something that you cannot experiment on. How do you experiment on a hurricane? I mean, you can create like a little hurricane in water, or like just have a little dynamic model, but, you know, with the amount of uncertainty with climate models, there's no way you can run all of the scenarios. The only way you can do this is to run these as simulations on a computer. How do you simulate a nuclear accident? It's like, you know, I guess they're laughing about making mess in your room. Okay. Okay, how do you simulate a coal boiler? How do you experiment on a coal boiler? It's really expensive. Every time we have a coal boiler facility downtown. Every time we want to run it, we have to run it for like 4 hours for it to warm up enough before we can take some measurements, and then we screw something up, and then we're like, oh man, we have to repeat the experiment again. So we'd rather do this on a computer in a simulation. How do you simulate flameless combustion? You don't know if there's a flame going on. Like flameless combustion is something burning without a flame. Like when you see a candle, even my 2-year-old son, he's like, he sees a candle, he tells me, it's hot, he doesn't touch it. He sees the fireplace, he doesn't touch it. You know, he pushes me towards it, and so, like, you touch it, you touch it. But with flameless combustion, there's no flame. You're sitting there and suddenly you're burning. So, you know, it's extremely dangerous. Things that take a lifetime, take decades, something called carbon mineralization, a process that takes place in nature. If you're like an outdoors person and you've gone into some underground caves with water kind of coming down, you see these beautiful formations in the ceiling. They're actually calcium deposits from the water as it seeps in, but these take decades to form, 1,000 years to form. So how can we run an experiment on something like that? So one project I worked on when I was a postdoc here at the U was carbon capture. So we wanted to take carbon dioxide from a power plant, essentially carbonize the water with it, and then precipitate it as calcium carbonate. And we wanted to understand this process of precipitation, but there's no way we could do it an experiment on that would take 1,000 years. You know, it's probably like my grandchildren would be, you know, collecting the results, and they'd be like, why is this stupid thing going on? Anyway, so, you know, we need to do these with simulations, right? So they're expensive, dangerous, impossible. I guess I made the point, okay? Simulation is a new kind of science. It's a new pillar in science. It's still not accepted as a pillar in science. So typically, if you talk to an experimentalist, they will tell you only observation is the key to science. If you talk to a physicist or a theoretical person, they tell you only the mind, the theory is the most important thing. But now simulation is starting to make its way as a fundamental pillar in the scientific investigation process. So we take this diagram, rip it apart, and add basic laws and simulation to this diagram. So essentially now experiment on little laws that we can understand. So how does nucleation happen, for example, when we're talking about precipitation? Or what are the kinetics in a star? So for example, we can run simple experiments to understand the kinetics, and then we put everything together and all the basic laws together and put them in a simulation, and that will help us with the hypothesis and modeling approach, okay? So let me show you some simulations. This is a code that I've called Wasatch, after the Wasatch mountain range that I've been working on since 2010. It's a few million lines of code. It does turbulence reacting flow simulations. What you're looking at is a pilot scale, just like this little small coal boiler. And what you're looking at here, these red streaks over here, they're coal particles coming into the coal boiler. And as they come in, there is heat in the boiler, just like because we're getting it started. These coal particles devolatilize, they emit gases, and then immediately the gases burn, and they generate more heat, which would devolatilize the new incoming coal particles, and so on and so forth. But we're looking at just kind of the flow inside the coal boiler, and the exhaust is way up there. So let me show you this now. If you take this plane, or essentially climb on top of the coal boiler and look down, okay, in real life, this is what you see. We call this the fireball. This is taken from a real coal boiler. That's probably 10 by 10 meters by 10 meters. And you see some smoothing because the shutter speed was so slow compared to how fast the gases were moving. It looks like it's a little bit smeared out, okay? Now I'm gonna superimpose on top of this, what the flow, what my simulation is showing. Getting started, and then you start seeing the formation of the fireball. Now, if I take an average over time of my simulation, it will fall approximately on top of what we observe qualitatively in real life, okay? So that's the power of numerical methods. I am able to look instantaneously at how the flow looks like, what the temperature, what the velocities are, how the particles are behaving, something that no experiment could give you. Literally, okay? But you gotta have the right models in your simulation, okay? I'll show you some other videos from the code, just kind of some eye candy. This was a project with mechanical engineering. They were looking at the flow of pollutants between two buildings. So if looking at the top view, this is building A and another building, and someone is standing here because it was cold and you decided to kind of hang out here, but there's some pollutant coming in over here. What happens? What the red is, think of dirty air essentially, and what happens in this little cavity. But this also simulates the flow over an open cavity. So if you have a sunroof or moonroof, whatever, you open it, you're driving, and you hear this, right, when you're driving. I don't know if anyone has experienced that. You see this this intermittency in the airflow. That's what's creating that noise, okay? And just a bunch of other simulations, just some eye candy. This was a project that I did with the military. This has to do with wave propagation. What you're looking here is at actually a helicopter that's emitting a noise, and that is approaching an enemy terrain, okay? And we wanted to understand the sound propagation so that we minimize or understand how sound propagates in enemy terrain. That's as much as I can talk about this project. But it was a fun project. Otherwise, I'll be in prison. Okay, so what does it take? What does it take? To be a simulation person, to be a numerical methods person, you have to be a jack of all trades, literally. You have to understand numerical methods, you have to understand programming, coding, some computer science, you have to understand engineering and physics, and you have to understand math. Okay? Now that's hard, but that also makes you a very unique individual. When you go and compete with others in the job market, in the end, you know, the college phase is going to be over, and you'll be like, uh-oh, you know, I need to get me a job, and, you know, a nice high-paying job for that matter, right? So anything that gives you some edge over others, okay, is going to be helpful. And, you know, this combo I find to be very attractive. I have colleagues who work for Goldman Sachs. What do they do for Goldman Sachs? They analyze, like, you know, investments for them in, you know, oil and you know, air pollution and crazy things like that, because they're engineers and they understand programming, and they do kind of, they apply their skills to things that are not just necessarily only engineering, okay? But these four things, I find them, well, anyway, I always wanted to be these four things, okay? But I kind of want you to also be these four things because it does give you an edge, okay? Okay, now we switch back to the course. Some survival tips. I'd like you to brush up on your programming skills like yesterday, okay? Just right now. And I'm gonna talk about a couple of guides that will help you. And as we go through the course, you know, I'll be giving you as much coding tips as possible, even, you know, some of the algorithms, you know, that we will be using. And excuse me, and I'll ask you to do some small modifications. But if you know a programming language, and if you know Python, all the better. Go and brush up on your programming skills right now. I will introduce Python, and we will work together, you know, but I come from a school of thought that my job here really is not to teach you. My job here is to inspire you and pave the way for you to learn. If you're like me, if I want to learn something, I have to get my hands dirty, I have to make mistakes, I have to fall and stumble and stand up. And I think a large majority of people learn that way, okay? And so I always, if you expect me to instill, you know, the material in you without you putting an effort to learn it yourself, that's not going to work. Okay, because there's just, you barely see me for 3 hours a week, or, you know, a little bit less than that, because this class is 1 hour 20 minutes rather than 1 hour 30 minutes. So, you know, you see me for less than 3 hours a week, and there's a lot to cover. So you have to rely on yourself to essentially learn the material. I will inspire you, I will pave the way, I will take down the hurdles from in front of you and help you do that. But it's on you. The learning is going to be on you. You have to make the effort. Sometimes your effort is inefficient, okay? And we will help you with that. We'll tell you, no, don't go down that road. For example, I see many students when we're trying to evaluate the exponential function, for example, we're making a plot over 100 points. They like write a line for each point. I'm like, no, that's inefficient. You're making an effort, but that's inefficient. We're going to use a for loop to do that, and we can do that in 2 lines, or even 1 line with vectorization with Python, okay? So those are the things that I will help you with, but you have to make the effort, okay? Start on your homework early. It's not high school anymore. You know, as soon as you get a homework, get started on it. At least read it, you know, that idea I told you, look at the homework, look at the thing, see what it's about, and then it will kind of sink in your mind. It would be great if you review class notes prior to the lecture and review them again after class, and I'll make an effort to post my lectures ahead of time, and so that you can get an idea of what to expect in the next lecture. Before doing homework, rework the examples that we did in class. We'll try to do as many examples as possible. And if you are stuck, get help. Again, I'm happy to answer your questions, but don't expect me. So if you come to me and ask me a question, I will answer you with a question, because I'm not going to exactly answer you. I want you to answer the problem. I want you to answer the question. Now, which question was that? So you come with a question, I'll answer you with a question so that you find the answer. So don't be upset when I do that. And the TAs will do the same. Okay, so you come and ask me, how do I evaluate the second derivative? My question would be, how do you evaluate the first derivative? And then you're like, okay, I do it this way. So how do I evaluate the second derivative? And then I'll ask you, what is the second derivative? And then you'll say, well, it's a first derivative of a first derivative. And there's your answer, okay? So that's my style, all right? Don't be surprised or upset when, that happens. And take advantage of the discussion help sessions. And if the forum kind of, starts growing, that'd be awesome. Then you can all help each other. Thoughts. My English is terrible today. Thoughts on homework. I used to actually say thoughts when when you learn English as a third language, you just kind of spell out, they tell you O and U is U, O, U, thoughts. And anyway, then you come to America and you're like, oh, okay, it's thoughts. Okay, so homework thoughts. Getting an answer is not the goal. Look, I don't care if you get the right answer. What I care is your interpretation of the answer. When I was taking heat transfer in my undergrad, our teacher gave us this, so I had a headache. I'm human too. So I had a headache before the exam, like a 1 week, really horrible headache. Didn't study well, didn't prepare well, even during the exam. And anyway, so I didn't do well in the exam, but I still got an A on that exam. So he had, I still remember this vividly. We had this problem, radiation heat transfer. He gave us two spheres in outer space. One was at 1,000 degrees, one was at 2,000, and he asked us to calculate the temperature in the middle. Very simple problem. And for some reason, I had like 15,000 degrees as my answer. I don't remember the number exactly. And I told him, this doesn't make sense. I mean, how could you have 1,000 and 2,000? How can you get 15,000 degrees in the middle? There's no way this could happen. I mean, at best, it would be somewhere in between, right? And I told him, this doesn't make sense. I don't know where my mistake is. He gave me full credit. Turns out I screwed up the Boltzmann constant by an order of magnitude or two. Temperature should have been 1,500. But anyway, that's what I want from you is, don't be after the answer. It's the approach to the answer that matters. And if you get an answer, I want you to analyze it and say, look, this doesn't make sense. I don't know where my mistake is. Especially on exams. I'll try to give you as much partial credit as I can if you show me insight, okay? I don't care about the final number. Because in the end, in real life, you're going to have a little bit more time and other people helping you kind of make sure you get the right answer, the right number. But it's the method, the approach, the analysis of the number and what they mean that matters. Writing code is not the goal. I don't care if you write code like I don't know, Shakespeare. He didn't write, but anyway. So the equivalent of Shakespeare. I don't want you to write Shakespearean code. I don't care. But the code needs to address the problem, and we'll work with you on making it a little bit more efficient. But again, this is not a class on coding or programming, and those two things are very different. But as once you get the virus of coding and programming, I guarantee you're going to get better automatically, naturally. Now, how you present your results is often as important as the results themselves. So, sometimes I see these reports with just like code and a number. What is this? I have no idea. The number doesn't even have units, or what it means. The plots don't have labels on the x-axis, the y-axis. Trust me, in my work, I spend 80% of my time just trying to present my work, okay, and the 20% actually doing the fun work. Okay, I know it's annoying to kind of format plots and make them look nice and presentable, but in the end, we are social beings, and that's how we impact each other. One day you're going to stand up in front of a bunch of people who are going to be squinting at you and looking at you in weird ways, and you want to try your best to kind of convey a message and or impress them. I don't know what you're optimizing for, but focus on presenting your results in the least complex manner, okay? So, and in the easiest way to understand. So, for example, plots, always label them. Don't put like 50 curves on one plot and they are all on top of each other. Or like send me a plot with like yellow curves. Yellow on white, it's like the most annoying thing. Anyway, so it happened. Okay, so now, but this is literally why engineers and good engineers make make a lot of good money. It's because they can sell the message. They're basing their results on a good foundation, and they, present it in a way that the average person can understand it, okay? And that's, if you can explain it to your grandmother, then you've hit the jackpot, okay? So always imagine, we have this thing as faculty members called the elevator pitch, when we go try to get money from funding agencies so that we can fund the students and give half of it to the university. So what we have to do, we have to do this thing called the elevator pitch. Imagine you're riding in the elevator with a person who gives you, a program manager who's going to give me money for my research. I have the length of an elevator. I go in and I press like the last button, try to kind of make it as long as possible. Essentially, I have 15 seconds to sell my research. 15 seconds, okay? And not only that, I have to sell it to someone who's not in my area. Program manager is like, doesn't necessarily work in the field that I work in. It's just like big, directorate in the National Science Foundation, for example. So you have to not only to explain it to your grandmother or someone sitting next to you on the bus, but you have to do it in 15 seconds, 30 seconds for you, okay? All right, so interpret your results well. Plots must always be labeled, okay? In the first couple of homeworks, I'll probably not deduct points on those, but if I deduct points on those, it's for your own benefit, okay? It's just to essentially teach you that lesson once and for all, okay? Numbers without units are also very dangerous, and most often, many times are meaningless unless the number itself is dimensionless. You will learn about dimensionless numbers further in your career. There's a great example here. If you click this, a link about the Mars rover. So Lockheed Martin is major defense contractor in the US. They were developing the Mars rover for NASA. And after a 10-month mission, was in 1999, I believe, the rover, everyone was excited, and the rover approached Mars, and everyone was waiting, and then the whole thing just burned just crashed and burned and got destroyed. Apparently, Lockheed Martin, they sent their numbers in British units, so pound, force, slug, whatever, and NASA interpreted those numbers, the code that NASA put on the lander, interpreted the numbers in SI units, and the whole thing crashed. So be very careful in your life with that. Numbers without units, unless they're dimensionless, are meaningless, okay? Okay. Now, my rant about programming. Okay, how many of you speak more than one language? Okay, very nice. Okay, so let me ask you this. When you want to express a thought in another language, what changes? Does the thought change, or does the language change? The language changes, right? That's exactly the same thing in programming. Think of programming, the programming language, it's called the language, as just a syntax to express an idea, a thought. For example, you want to sort an array. Well, obviously, you can sort an array in C++, in Python, in MATLAB, in Perl, in Java, but you're still sorting an array. So the programming language itself is only an expression of a thought. Therefore, what matters is the thought itself, rather than the language itself. The language is only the clothing that is placed on the thought that delivers the thought. So if you know what you want to do, if you say, hey, I need to right now rank these numbers for this numerical method, or I need to find the root for this equation, the next step would be, how can I find root finding in MATLAB, or root finding in C++, or root finding in Python? And it's just syntax, therefore. Just like you would go and use the Google language thing. You would type in the thought you want to express, and you can find it in different languages. Because the thought itself doesn't change, but it's the expression of that thought in the language that changes. So I want you to think of programming as just simply that. What matters is what you want to accomplish first. If you can step away from the problem and say, okay, over here I am going, so let's say I give you, and that's one of the homework problems, I want you, one of the homework problems we're going to deal with is a set of gas stations in Utah that are cheating on, the gas meter, and I want you to I give you 4 gas stations, and I want you to calculate the error connected in the gas meter, in the gas station's meter. And what you want to do then is loop over the gas stations and calculate the errors. Okay, so that's the idea here, is to loop. How do I loop over a list of things? So you can then ask Google or your colleagues, or look up the documentation for Python, for example. Say, how do I do a loop in Python? How do I do a loop in MATLAB? Does this make sense? To this day, I do this because there's no way I can memorize my preferred coding tool is C++ for like the heavy-duty research applications, but I always prototype things in Python. And to this day, I'm like, I don't want to take up disk space up here to remember how I sort an array in Python. I can just Google it every time I need to. It's just like looking through a reference book. But what matters is that I know I need to sort an array, or I need to do a for loop over here, or I need to do a while loop. Does this make sense? Okay. So the programming language is just that. A language, its purpose is to deliver a message. The language itself should not be your concern. If you know what your program is supposed to accomplish, then you express that in any programming language. I think this is it. If you don't see it yet, I think this is a very powerful message, okay? And let me say that I need to substitute the word programming with coding. Coding is just a technique like driving. So you can drive a car, but you don't need to understand how a transmission works, how the internal combustion engine works, how an alternator works, right? You can still drive a car. It's a skill. So coding is just that, like driving a car. Programming is more involved in essentially the computer science aspects of code development, okay? So you'll find many programmers who are not computer scientists, Computer science is the science of talking to computers, right? And you can get there as you mature as a coder. But as an engineer, you don't need to go beyond knowing how to write a basic code that does a certain number of things, okay? Now, I recommend you use this approach to write code for your problems. Just sit down and say, okay, what do I need to do here? I have these 4 gas stations. I need to, loop over them. Now, to loop over them, I need to put them in something, an array. How do I create an array in Python? And therefore, that's how you need to approach your problems. Just try to think about what you want to accomplish, and then just go and search the documentation, the internet, ask your colleagues how to do something, okay? Now, why did we go to Python? Okay, it is free forever, and that is really nice, right? It's forever free. You guys used to pay like $20 or something per semester for MATLAB, and then in the hopes that you graduate, work for a big company, and then you tell them, hey, I only know MATLAB. You have to buy like $1 million license for MATLAB. That's not the case anymore. For what it's worth, MATLAB is only becoming more and more limited because right now Python is taking over. And Python is not going to reign forever. In 10 years, there's going to be even higher level programming languages. But, that's a problem for future numerical methods students. Okay? It's very easy to get started programming with Python. Literally, like, things just work in Python. It's like you just try something. And sometimes just like you can add watermelons and cantaloupes in Python. The result doesn't necessarily make sense, but it will try to do it for you. And many studies have found that feature in Python is what makes it so attractive to newcomers, because it allows you to have results, to feel that you're doing something, right? Just like when you're that's what's the beauty of programming or computing, is that you get immediate results compared to experiments. I'm not an experimentalist because I am impatient. I cannot wait for an experiment with a bunch of rats and things and slimy things to run for like 10 days and then come and say, oh man, it didn't work, so I have to repeat it again. With computing, you can get immediate results. And so the same thing applies with Python, is that you can try things and it just works. It's very forgiving, okay? Python is in very high demand. I'll show you some recent numbers. In fact, it's ranked #1 right now. Depending where you look at, IEEE Spectrum is ranked #1. On Indeed.com, it's ranked #2, just barely under Java, with a difference of about 2,000 job postings. But then, like, MATLAB is way at the bottom. Okay, so this is really good. Python is very forgiving. And there's a significant community support around it. So you can Google pretty much anything you want to do with Python, and you'll find it on the internet. There's Stack Overflow and just Google, essentially. And you can even use Python in a web browser, and we will be focused on this. All you have to do is open up Chrome or Safari or Explorer and point to a website, and you can start programming. No need to install anything. We work hard to get this to you, and use Google to learn how to code in Python. Again, more on that after we finish with the introductory slides. Okay, a few tips on solving problems. Clearly define what you know and what you do not know. So again, when I ask you, I give the problem of the gas stations. Your goal is to find which gas station cheated you more than the others, which means you need to find the error in the meter of each gas station. What do you know? You know the measurements given by each gas station, and what you need to compute is the error. Okay? So clearly define that. Write down a solution procedure or a series of steps, to obtain the unknowns given what you know and what you learned in class. So I'm not going to give you, homework that is going to require you to study celestial mechanics. I'm going to give you homework based on what we discussed in class. I'm going to challenge you a little bit, okay? Just kind of pull you out of your comfort zone just a little bit, okay? But still, you have all the tools that you need to be able to solve the problem. And when possible, separate and compartmentalize the various aspects of the problem. Like say, I'm going to put the gas stations, the numbers given by the meters gas stations over here. I'm going to compute relative errors over there, and just kind of try to structure your solution process in steps. Okay, first we're going to do this, next we're going to do that. And that works for many people. For me personally, that doesn't work because my mind is very nonlinear. I kind of think from the end and the beginning and then the middle. And so, but I'm trying to give you a strategy if all else fails. If you follow this strategy, it's a rational strategy that will help you try to get the solution. Now, before you go on and start programming, try to run the solution by hand. So, for example, if I'm asking you to do the Thomas algorithm for 1,000,000 equations, the Thomas algorithm you're going to learn is a direct solution method for systems of linear equations, okay? Obviously you're not going to be able to do 1,000,000 equations by hand. You're going to do that in Python. But first, to test your knowledge, do it on a couple of equations. Just like imagine 2 equations, okay, and just try to run the algorithm by hand and verify your code with that solution by hand, okay? So that you're confident that your code works on the problem that worked by hand, okay? And then plan your numerical implementation. It's not necessary, but many times as you're writing code, you find yourself that you have to repeatedly use the same thing. So for example, we're going to be computing derivatives and integrals, okay? And for different functions. So the integral calculation or the derivative calculation is the same independent of the function. So what would make sense then is to create a little Python module or Python function that you would call with different functions, sines, cosines, exponentials, etc., to compute the derivative. Okay? You don't have to do that, but it will make your code much more efficient and easier to read. Okay? And these slides, by the way, are posted on my website already, so you can go on my website and see actually the next few lectures are already posted there. Again, test your code on a simple example, the one that you did by hand. So going back to the Thomas algorithm for the linear systems, you did that by hand on a couple equations, and then you wrote the code. You want to test the code for 1,000,000 equations. Well, first test it on the 2 equations, right? And make sure you get the same answer that you got by hand, okay? All right, so do you have any questions on these introductory slides so far? Okay, any concerns?